Okay, guys, so a lesson here on unbalanced forces. Before we talk about unbalanced forces, let's just remind ourselves what a force is. A force is just a push or a pull that causes motion. So a push or a pull that causes motion. In real life, all objects have a bunch of forces acting on them all at one time. So in this particular situation, you have the car's engine is pushing it forward. You have the wind resistance creating friction against the car. You have gravity pulling it down. You have friction on the road, and you have the earth pushing back on the tires. So all of these forces add up together. On an airplane, you have this lift force that keeps the airplane in the air. You have gravity pulling down, the jets for the engine push it forward, and the wind resistance drags against the aircraft. And then a fish, pretty much the same thing. The buoyancy causes the fish to want to float up. Gravity wants to hold it down. Friction works against it as it swims in one direction. All right, so the question is, if there's all those forces acting on an object, how do I know which way an object is going to move? And the answer is that if you add up all of the forces that act on an object, if the total is not zero, the objects will move in the direction of the greatest force. Okay, so we're going to look more about that. That's where this idea of unbalanced and balanced forces comes in. When you do add up all the forces, the total that you get is called the net force. Okay, and that net force will determine which way the object moves. Okay, so when you add up all the forces, if you get zero, okay, then we say those forces are balanced, which causes motion to not change at all. So whatever the object was doing, it's going to keep on doing that. Okay, there's no acceleration. So again, add up all the forces. If there's zero, the object's going to keep doing that. When you add them up, if you get a number that's not zero, then we say that the forces are unbalanced, which means there is going to be a cause in motion to change. And we call that acceleration. Okay, so net force, you add up all the forces. Zero means no change. More than zero means change. Okay, so we're gonna prove this to you real quick. We're gonna look at a simple interactive here. By the way, you can click on these in the PowerPoint that's in the assignment on Canvas. You can click on these and you can do these same activities here yourself. But I want to prove to you that unbalanced forces do cause the object to speed up, slow down, or change direction, and balanced forces do not cause a change. They keep the constant speed or constant direction. Okay, so let's look at that now. I'm going to go ahead and click on these, and that way we can see the sum of the forces is another word for net force. So this cart right here is at rest. You can see that because it speeds at zero. And the net force is zero. Remember, we said if net force is zero, then the object's going to keep doing whatever it was doing. So this object is at rest. It's still. It's going to keep on being still as long as that's zero. Okay? But if I change that to not zero, now you can see the sum of my forces is 50 newtons to the right. So that means this cart should move when I click go. And it is. So this is a change in speed. You can see the speed going up, and it's a change in direction. That's because the forces became unbalanced. They're not zero anymore. So we know now that if an object's at rest and you unbalance the forces, it's going to cause the object to move in the direction of that force. But what happens if the object's already moving? All right? And they become balanced. So I'm going to get this moving, and then I'm going to balance it. Notice that it's zero again, right? So the object's going to keep doing whatever it was doing. Well, what was it doing? It was moving. It was already moving. And so when I balance the forces, that object's going to keep the same speed in the same direction. There's no change. And it'll keep going forever and ever until the forces become unbalanced again. So let's unbalance them. Now we have a force going the other direction. Okay, I'm going to balance them back. They're balanced again, and you can see that the cart's going to stay at that same speed, same direction. Okay, so what would happen if I threw him on there and him on there? Well, they're balanced, and so the cart's going to keep doing whatever it is. Okay, so again, this proves that unbalanced forces cause a change in the motion of an object. Balanced forces cause no change in the motion of an object. Okay, now, so we don't have to draw the cars and the airplanes and the fish and all those things and the carts. What science does is we just use these boxes. These represent an airplane or a car or any object at all. They're called free body diagrams. That's just a name that means a box that's supposed to represent something else. Okay, so students, you guys, if you can look at this page and you understand how they got 0 on this top problem and 20 newtons on this second problem and then 2 newtons on the third problem, if you get that, you can skip this video ahead 5 minutes, okay? Because in a moment, I'm going to have a teacher's going to explain how to calculate net force. But if you can already do that, you don't need to watch this next part of the video. When you see SpongeBob SquarePants, you need to stop the video and start playing it there again. Okay, so here we go. This is how to calculate net force.
The big important things here, if the forces are acting in opposite directions, we're going to subtract them. So we've got a force to the right, a force to the left, they're opposite. Again, a force to the left, a force to the right, they're opposite. So whether they're pushing against each other or pulling away from each other, those are opposite forces, and you're going to subtract them. If the forces are acting in the same direction, then you're going to add them together because they're working together to move an object or attempt to move an object in some direction. It doesn't matter if the two forces are coming from the same side or from opposite sides, like one is pushing and one is pulling. Either way, they're acting in the same direction, so you will add them. All right. Let's remember our unit of force, capital N, the Newton. If we look at our first picture, we have a force to the right and a force to the left. So these are opposites, and that means we need to, opposite forces, subtract them. So I will do 40 newtons minus 40 newtons, and we get 0 newtons. So the net force is 0. Which means that there's going to be no movement. And going back to our vocabulary, these are balanced forces. Okay, there's no net movement, no net force. The next example, we also have opposite direction forces. You can see I drew one force arrow a little bit larger, darker, because it's a greater force than the other. They are in opposite directions, so we need to subtract them. So I'm going to do 60 newtons minus 40 newtons, and our resultant force, or our net force, is 20 newtons. Now, these forces are not balanced. There are different size, different magnitudes, different strengths of forces, so they are unbalanced. And direction is important, okay? My greater force, my force with a higher magnitude is going to the left. So that 20 newtons force is going to be to the left, okay? Make sure you know your directions. This is right side, this is left side. The direction is towards the left. All right, our next example. We have forces going in the same direction. And again, according to your notes, which you should keep referring to, forces that are moving in the same direction, we're going to add the forces together. All right, so in our first example, we have two forces going to the right. So we have to add them, 40 newtons plus 40 newtons, and you get 80 newtons. Again, these are unbalanced because they're not acting opposite of each other in a way that's not going to cause motion. And this is 80 newtons to the right. All right, and then the next example, we have a push force and a pull force, but they're still moving in the same direction, so we're going to add them together, 50 newtons plus 40 newtons, and that will be 90 newtons. And again, that's to the right. All right. And then our last example. In this one, we have 3 different forces, so we need to break it down. Okay, we see some that are going to the right, some that are going to the left. In this situation, I have 2 forces that are both going to the right, so I'm going to take those and I'm going to add them together first. So this force on the right side pushing to the left is a total is 100 newtons to the right, and at the same time I have 40 newtons to the left. All right, so now I need to subtract them because I've got 100 newtons going in this direction, I've got 40 newtons going in this direction. So I'll do my 100 newtons minus 40 newtons, and I get a total of 60 newtons. Okay, my bigger amount of force is to the right, so that is 60 newtons to the right.
All right, guys, so now that we know how to calculate net force, if they give it to us, right? But what if we don't know the net force? What if we don't know the force on the object? Well, there's a way you can find out, and the next part of this lesson is how to do that, okay? Good news, there is a formula. Just like there was a speed formula, there's a force formula, okay? And the force formula is force equals mass times acceleration. So the net force equals the mass of the object multiplied the amount of acceleration. Now here's the cool thing. We can use a triangle, a magic triangle, just like we did for speed on the force, and it'll help us solve a bunch of stuff. All right, so let me go back real quick. If you'll notice that to get force, you have to multiply mass and acceleration times each other, okay? That means that mass and acceleration have to be on the bottom because you multiply those two that are on the bottom. And that means that the force has to go on top, okay? So if I want to find force, then I do the other two, which is to multiply mass times acceleration. That's how I get this formula right here. If I want to find mass, then I do the other two, which is force divided by acceleration. That's how I get the mass, force divided by acceleration. And then lastly, if I want to find acceleration, then I do the other two, which is to divide the force by the mass. And that's how I got this problem right down here, okay? So that's how we use the magic triangle for force, just like we do for speed. Okay, but you're going to be given some word problems, and they might not tell you, hey, this is the force, this is the mass, and this is the acceleration. So how can you make sure that you're using the right numbers in the right place? Here's how. Anytime they give you force, it will be given with an N for newtons, okay? Anytime they give you the mass, it will be in the unit kilograms. And anytime they give you the acceleration, it'll be in m/s squared, meters per second squared. So that's how you know you can look in the word problems and get the right numbers and plug them in the right place. Let's look at an example. An ancient army was using a catapult in battle. The soldiers loaded an 80-kilogram boulder into the catapult and launched it at 5,000 meters per second squared. How much force did the boulder strike the enemy castle with? Okay. So let's go and look for the numbers in there, see if we can find out how to plug this in. Same problem here, I'm just using different color, okay? So the soldiers loaded an 80-kilogram boulder. Well, kilograms, we said that is the mass, so that means they're giving us the mass there. Into the catapult and launched it 5,000 meters per second squared. Well, meters per second squared is acceleration. So they just gave us the mass and they just gave us the acceleration. That means that they have to be asking us for force. So let's see if that's true. How much force, there it is, did the boulder strike the enemy castle with? Okay, so we're going to use this formula, force equals mass times acceleration, to solve that problem. So we need the mass, we need the acceleration. So the mass was 80 kilograms and the acceleration was 5,000 meters per second squared. When we multiply 80 times 5,000, we get 400,000 newtons. That's a bunch of force. And just so you can kind of have an idea at home how much of a change that is, that's like taking this 80-kilogram boulder and turning it into a 40,789 kilogram boulder. So ton of force there. All right. So now you know how to do net force, and if you don't, and now you know how to find the force if they don't give you the force, right? So let's go do some practice problems. All right. So go back to Canvas and look for the calculating force and net force practice problems and see if you're able to calculate that on your own.